Welcome. In this video, we'll explore linear regression, one of the simplest yet most powerful models in data science. By the end, you'll understand what it is, when to use it, and how it learns from data. Linear regression is a supervised machine learning algorithm. Supervised means the model learns from labeled data. We give it both the inputs and the correct outputs during training. The goal is to find a linear relationship between those inputs and outputs, often represented by a straight line. For example, we might train it to predict a person's weight based on their height. Once trained, the model can estimate new values it has never seen before. Linear regression is used for problems where the output is a number, not a category. It can predict things like house prices based on surface area, patient blood pressure from medical measurements, or sales volume from advertising budgets. Any situation where the target variable is continuous and has a roughly linear relationship with its predictors is a good use case. Even though linear regression is a machine learning model, it still follows basic statistical assumptions. The data must show a roughly linear relationship. The errors, the differences between predicted and actual values, should be normally distributed. Strong outliers can distort the model, so they should be checked. And finally, the input variables should be reasonably independent from each other to avoid misleading patterns. In supervised learning, the algorithm learns from examples. It starts with a random line and predicts values for each data point. It then compares those predictions to the real outputs, the labels, and calculates the error. Using a process called gradient descent, the model slightly adjusts the line to reduce the total error. This continues until the line represents the best possible fit. Essentially, it learns the equation that minimizes the difference between prediction and reality. To summarize, linear regression is a supervised learning algorithm used to predict continuous outcomes. It learns from labeled examples, adjusts itself to reduce error, and produces a mathematical equation that best fits the data. Although it's one of the simplest models, it forms the foundation of many modern machine learning techniques. Understanding it is a crucial first step toward mastering predictive modeling. Now let's start to build our first linear regression model using Python and scikit-learn.
Welcome to Linear Regression for Everyone. Have you ever wondered how websites like Zillow can instantly estimate house prices? Or how apps predict things like car values or health metrics? In this course, you're going to build the brain behind that magic. We'll create a simple AI model that can predict house prices based on basic information. The best part? No complicated math needed. We'll use Python to do all the heavy lifting for us. By the end, you'll have your own house price predictor that actually works. Now, let's dive into some hands-on coding. First, we need to import our tools. We're bringing in the California housing dataset directly from scikit-learn, and we'll use pandas to work with our data in a structured way. Next, we load the actual housing data. This gives us a ready-to-use dataset without any complicated file downloads. We then convert this data into a pandas data frame, which is like a smart spreadsheet that Python can easily work with. You'll notice we're creating a new price column. The original target values are scaled, so we multiply by 100,000 to convert them to actual dollar amounts that make sense in the real world. Finally, let's take a quick peek at our data. We'll print out how many houses we have in our dataset. It's over 20,000 California neighborhoods. Then we'll look at the first few rows to see some example income levels and their corresponding house prices. This gives us a tangible sense of what we're working with. Now let's bring our data to life with a visualization. We're using matplotlib, which is Python's go-to library for creating charts and graphs. First, we create a figure with a nice size, 10 by 6 inches, giving us plenty of space to see the patterns clearly. Next, we create a scatter plot. Each blue dot represents one California neighborhood. On the horizontal axis, we have median income measured in tens of thousands of dollars. On the vertical axis, we have the actual house prices. The alpha value of 0.4 makes the dots slightly transparent, so we can see where points cluster densely. We add clear labels to both axes so we know exactly what we're looking at. The x-axis shows median income and the y-axis shows house price. We give it a descriptive title that tells the story: California, How Income Affects House Prices. Finally, we add a grid to make it easier to read the values, and then we display the plot. Look at that pattern emerging. You can already see the general trend. As income increases, house prices tend to increase too. Now for the most exciting part. We're going to train our linear regression model. First, we import the linear regression model from scikit-learn, which gives us all the machine learning tools we need. We prepare our data by splitting it into two parts. X, which contains the feature we use for prediction, that's median income, and Y, which is what we want to predict the house prices. Think of X as the input and Y as the output we're trying to learn. Next, we create our linear regression model. It's like creating a blank brain ready to learn. Then we call the fit method, which is where the magic happens. This is when the model analyzes all our data points and finds the best possible straight line that represents the relationship between income and price. After training, we extract the learned parameters. The slope tells us how much the price increases for each unit increase in income, and the intercept represents the theoretical starting price when income is 0. Finally, we print out our magic formula. This equation is what our model will use to make predictions. It's the mathematical representation of the pattern it discovered in our data. Now let's visualize our model's understanding with a minimal clean plot. First, we create a figure that's 8 by 5 inches, a nice compact size that shows everything clearly. We start by plotting our original data points as a scatter plot with low opacity, so we can see where points cluster together densely. These are the actual income and price combinations from our California housing data. Next, we plot our regression line in red. We generate a range of X values that cover our data spectrum, then use our trained model to predict the corresponding Y values for each point in this range. The R dash means a solid red line, and we make it thick enough to be clearly visible against the background data points. We add basic axis labels, though in a real presentation we might make these more descriptive, and turn on the grid to help our eyes follow the values accurately. Finally, we display the plot. There it is. The red line shows exactly what our model learned. The straight line relationship between income and house prices that best fits all our data points. Now let's put our model to work. We'll test it with 3 example income levels, $30,000, $60,000, and $100,000. We feed these to our model's predict method, and it instantly calculates the expected house prices for each income level. We then print out the results in a clean, readable format that shows exactly what our model predicts for each neighborhood type. Finally, we measure how accurate our model really is. We use mean absolute error, which tells us the average difference between our predictions and the actual prices. This gives us a concrete number, in dollars, that shows how close our model gets to reality on average. Now let's upgrade to a multi-factor model. Instead of just using income, we'll also include house age and average room count. We create a new set of features that combines all 3 factors. We initialize another linear regression model, then train it using all these features together. The model now learns how income, age, and rooms collectively influence house prices. This gives us a smarter model that considers multiple real-world factors simultaneously. Let's examine our multi-factor model and create a visualization. First, we extract the coefficients. Notice that for income specifically, the slope is different now because the model is considering multiple factors together. Since our multi-factor model works in higher dimensions, we can't easily plot it as a single line. So we create a temporary single-feature model using just income, purely for visualization purposes. We generate a smooth range of income values and use this temporary model to create a regression line. Then we plot both the original data points and this red trend line, giving us a clean visual representation of how income relates to price when considered in isolation.